So good day, welcome to our final presentation. We are Element 79 Mining Corporation, and today we're presenting to you on the design comparison of a mineral processing and hydrometallurgy processing plant for gold ores. For the agenda today, we'll get into the project introduction, then we'll get into the preliminary design, the detailed design, along with this evaluation, then we'll get into the HSEQ, and then the final plant design recommendation, and then questions at the end. So we'll get into our project introduction. First is about the team. My name is Zachary Mullen. The rest of the team consists of Josh Banfield, Thomas Crummell, Justin Dwyer, and Adam Wicks. So for the problem statement, our main objective is to perform a processing design comparison that will produce a quality grade gold product from the Ming mine in Bay Bird, Newfoundland, Labrador. And the two designs under consideration are mineral processing, so flotation, and hydrometallurgy, which is leaching. We have certain targets and deliverables, one being head grade of 2.3 grams gold per ton, a minimum target grade of 0.6 grams of gold per ton, and capacity of 2,000 ton ore per day. So for our project motivation, hydrometallurgy is still in its infancy stages. So with the downfall of the petroleum industry, other resources are now being exploited, and this project covers a wide range of areas that we've seen in our academics. So here's our work breakdown structure. As you can see underneath each of the names here, that each member was assigned a certain role within the team, and they had their associated tasks completed for this term in particular. So here's our project Gantt chart. As you can see, all of the critical path items have been completed, as well as the other subsequent items. The team then remained on task or ahead of schedule throughout the term. So next we'll get into the preliminary design.
So here's a block flow diagram of our process. We start off with our crushing stages and grinding stages, which are the same for both the hydromet and mineral processing. And then from our hydrocyclone, we branch off into our two different processes, one being the leaching side of things, which is the hydromet, and then the mineral processing goes to our flotation circuit. So we just investigated some raw materials to select for the size reduction operation. As well as for our leaching absorption, we have some raw materials and additives such as cyanide solutions. And then for our leaching lixiviants, we did do a technical comparison matrix to determine which one would be the best. And halides did win in the matrix, but due to cyanide being so predominantly used in industry, we decided to go with that one. And for absorption, we're using activated carbon for our absorption material.
Raw material and flotation, there's many, but the main being collectors. We decided to go with potassium methyl as the collector, and potassium methyl was chosen. It's lower cost compared to other brand name reagents.
And as you can see here, we just have our comparison matrix that we use to determine our materials we use for our different routes. And next we got into our conceptualized plant location. So some of the factors we chose in picking our plant locations are above, and then we have our 8 locations down below. And this is just a map of the 8 locations. So we have 4 in Newfoundland, 2 in Nova Scotia, 1 in Maine, and then our last one over in Ireland. So this is just our technical comparison matrix we used to determine our actual finalized plant location. And as you can see here on the side, it's just it's broke down on the weighted scores, and then we get a score out of 100. And New Era was the best. Right here is our flotation PFD, so I'm going to go a little more into size reduction area. So this is our size reduction, our PFD. As you can see, we have our primary crushing and secondary crushing, which is followed by our ball mill and our sag mill, and finally our hydrocyclone that goes on to flotation. Now Justin's going to take you through the flotation section.
Okay, so next we'll look at the flotation portion of the process flow diagram after size reduction. After size reduction, the slurry is mixed with water to produce a 25% slurry. It is then brought to the first bank section, which is composed of 3 reactor cell systems, which are flotation machines. In this battery condition, the product streams are mixed after, and we're assuming around 70% of the total gold recovery is coming out of each respective tank. The tailings, the rest is then sent to the second bank section, which is in the lower corner here. This is known as the scavenger bank, and it'll get some of the smaller particles out of the stream. There's a recycle stream of 25%, which brings the recovery to around 89. And that is recycled right before the first stage. And then the rest of the gold is mixed with the products from the first bank section, and then the rest is brought to the wastewater treatment section. So I'm gonna pass it off to Josh to talk about leaching.
Okay, so for the leaching design, for the hydromet design, the size reduction portion of the PFD is exactly the same, so I'll skip over that as Adam's already talked about it. So I'll go straight into the leaching section of the process, which is consistent of 6 leaching agitated tanks in countercurrent arrangement between overflow and underflow. So right now we use about 100 tons per hour of solvent to leach out the gold solids from the powder from size reduction. And this is using various assumptions, assuming that equilibrium is reached inside each tank, which we know it is because the tanks are oversized. And we also know that if there are no solids in the overflow and there's a constant underflow, then we know that these assumptions are also valid in this range. So basically what we have here is just a mass balance between stage 1 and stage I. So knowing that this equilibrium is established, as well as the other conditions I just mentioned, we can use a mass balance to determine the composition and the flow rates of each stage. So here is a graph of the final product. So as you see, we can step down between our operating line and our equilibrium line to give us the data values that we obtain in the chart on the right corner. So once this solution is leached out, we then have to adsorb the gold solutions into 2 sorption columns so that we can recover and concentrate the gold solution. So right now, we have 2 sorption columns which have a lower capital cost and a lower operating cost, but has a downfall of being semi-continuous. So what this does is actually removes out about 145 ppm of gold after the desorption process. So once that is completed and we have desorbed the gold off of the fixed bed, we then have to electrowin the gold ions out of solution into a solid gold product for sale. So we have 2 electrowinning bays that run in parallel. So the flow from the desorption step is split in half. And what this does is it uses, if you go to the next slide, it uses 2 chemical reactions, a redox reaction, oxidation and reduction, as shown right here. And this will actually give you the values of the solid product as well as any of the wastewater that is produced. So if we go to the next slide, we can see that using the equilibrium relationship as well as some stoichiometry, we can find the extent of reaction and then determine how much gold is actually being produced from this stage. So I'll hand it over to Wix for the detailed design to start off.
So this is how we determined our flotation cell sizing. So from literature, we found our total volume of our cells to be given by the flow rate times the retention time and a scale factor, then divided by 60, which is a constant, and times by the aeration factor, which is also a constant, and we ended up with a volume of 46.79 meters cubed, which would give us around 5 cells. So as you can see here, we use the RCS10 column. From this and using literature, we found that our height would be 3.61 meters, the diameter of 2.6 meters, and finally a width of 2.85 meters. And finally, we had determined our operating parameters for our flotation cells. So we found that our operating pressure would be at 1 atm, along with a constant temperature at around 25 degrees, so room temperature would give us our best yield.
So I'll go over the adsorption detailed design. So using an incremental mass balance around the fixed bed, we can determine that the concentration of the void space plus any concentration in the adsorbed part of the bed in the pores must be equal to the change in concentration throughout the bed. So this gives us a model that we can use to model the process over time, because as I said earlier, it is a semi-continuous process. Next slide, please. So here we just have the model parameters discretized. So we have an unsteady state equation, and we just discretize that so that we can actually solve it using a code in MATLAB. So once we have that completed, we have 3 different cycles. We have an adsorption step, a desorption step, and a regeneration step. The adsorption step strips the gold from the solution and loads it onto the carbon bed. The desorption step does the exact opposite and removes gold. And the regeneration step is just to reactivate the activation sites. So right now, the adsorption step runs about 230 hours and the desorption step about 24 hours. We did not go into the regeneration process, as the temperature in the desorption step should be sufficient to actually regenerate the bed simultaneously.
So the next step in our detailed equipment design was actually coming up with material to actually use within the process. That's due to the fact that the process utilizes corrosive materials such as sodium cyanide, hydrogen peroxide, potassium methyl xanthate. So research was conducted into several materials and also based on the group, the knowledge of the group, such as fiber reinforced polyester, alloy 6MO, 316 stainless steel, etc. So in order to properly evaluate each of these materials, a technical comparison matrix was developed, showing different criteria along the left-hand side there. So corrosion resistance and cost were the top two weighted criteria. So those were the most important to the process itself. And so here's our fiber reinforced and alloy 6MO technical comparison matrix. And based off the scoring, fiber reinforced polyester was the optimal choice.
So for the process simulation, the team investigated HYSIS and Aspen Plus in the beginning stage of the process, and it was determined this was not successful due to solids handling. MetSim was also investigated, and it seemed to be an optimal solution. However, the team didn't acquire a license or enough time to learn the program. Mass and energy balance for the Hydromet design were automated using MATLAB, and Excel was sufficient for the mineral processing. For the 5 main areas, size reduction, leaching, adsorption, desorption, electrowinning, capable of calculating production rate, efficiency, and profitability. These were calculated in Excel for the mineral processing side of the process.
So now I'm going to get into some control parameters for the flotation. Two main ones were the pH and the temperature. So that we developed the P&ID just with a few different instruments such as flow control valves, level and temperature and pressure indicators, as well as a PSV for pressure safety.
And then for the adsorption P&ID, we have 3 main control parameters. One being Fallon's, which can actually change the rate of absorption. And the next one being temperature, so as your temperature increases, your absorption rate increases, as well as your slurry density. So as you increase the slurry density, this results in a decrease in your adsorption rate. So in developing the P&ID, we took all those into consideration. So we put in certain controllers for temperature, and we also have controllers in for pressure as well as level. We have a water stream put in to actually control the slurry density. We also have safety features such as PSVs as well implemented. Next we'll get into the design evaluation of the project.
So first we look at the sensitivity analysis for flotation. This was completed in Excel as previously mentioned. So the sensitivity analysis is completed on particle size in this section right here, and this is for a 20-year life of mine. So pH and quantity of collector and agitation speed were also considered. However, due to lack of resources as well as resources illustrating that for this type of ore they had negligible effect. However, these can be considered with proper lab testing. So as you can see, there isn't much variation due to particle size. And if we look on the next slide, we can see that residence time also doesn't have a huge impact on size, and the most profitable to where our residence time is now, which is around 15 minutes. So flotation, as previously mentioned, lab testing would be optimal for creating an optimization. Right now, the process is optimized to about 89% efficiency with a 25% recycle stream, which is higher than our goal of 86%. However, with testing on tailing, concentrate, the mat, and the metals in these different streams, optimization could be done to make this process more efficient.
Okay, so I'll go into the Hydromet design and the process optimization. So here I have 2 tables, the nominal conditions as well as the prices used for the economic optimization. So we have various conditions. So basically the profit is equal to the revenue minus the expenses. We can determine that the revenue made is the amount of gold produced times the gold price, and the amount of expenses is just equal to the amount of reagents we use times the flow rates. So what we have here is a sensitivity analysis between the cyanide flow rate as well as the desorption flow rate for the solvent. So as you can see, at low flow rates, we can see that the Gold does not actually get removed from the solution, is not concentrated, and at high concentrations we're actually overdoing it and it's too much overkill. For the adsorption duration and the desorption duration, as the time is increased between the adsorption step, we actually have more gold leaving as a raffinate, and we're losing that concentration and thus losing profit. For the desorption step, the longer we run it, the more gold we get out of the fixed column and the more profit we get. So for the optimization, we use three different optimizers to be used: a pattern search algorithm, a genetic algorithm, and a gradient-based algorithm towards the end. So for the results of the optimization, we actually had similar results between all three trials, which was as expected. And so we can actually determine that the optimal conditions final optimized results were 99,370 for the cyanide flow rate for leaching. For the desorption step, 1,000 kilograms, which was the minimum for the optimization step, was achieved.
So then I'll get into some profitability analysis the team completed. The three main ones were the payback period, the return on investment, and the net present worth. And the equations for each one of these are seen here on the screen. So for this, as the gold price fluctuates daily, the team decided to do 5 different cases for a gold price. One being low, which is 20% less than an optimized. An optimized price, which is the price of gold we use for the optimization. A current price of gold, which was taken on March 7th of 2018. A high case, which is 20% more than the current, and an extreme high as well. And all the prices are in Canadian. So here is our results from our profitability analysis. The return on investment, payback period, net present worth was calculated for each.
So for the mineral processing stage, Excel was used to develop production profiles for the life of the mines of 15, 20, 25, and 30 years. So for the production profiles, as you can see, the initial head grade was 2.3 ppm, and then it goes down linearly to 0.6, which is where we cut off the mine. So we assume a straight line depreciation of gold. As you can see, we used the 20-year as a basis in this example. Over the 20-year period, it goes down linearly in both cases of hourly revenue and daily production rate. If we go to the next slide, we can see the annual cash flow. This was based on a gold price of $50,000 per kilogram of gold on a 20-year mine life. So there's a very low FCI for flotation, meaning that the plant is basically making a large sum profit immediately after the first year until the end of the lifespan.
So for the hydromet side of the economic assessment, we used the same 15, 20, 25, and 30-year life of mine, and also did a sensitivity analysis on the market prices that were used in the optimization. So again, using a 2.3 ppm gold head grade and a 0.6 ppm gold cutoff grade, we can determine the production profile, the production efficiency, and also the profitability over a range of the life of field. So for the price sensitivity, obviously the amount of revenue that you make is completely dependent on the amount of money that you get for your product as well as for your reagents. So we did a sensitivity analysis on this, this topic. And so we can determine that as the gold price increases, we actually see a very sharp increase in the profitability of the process. And then for our cash flow analysis, we actually lose a lot more money compared to the mineral processing process design, purely because of the amount of reagents and the amount of fixed capital investment that is required for this design process.
So now we're going to get into the HSEQ part of the thing. So right here we have our HAZOP study initially. So the first part of the HAZOP was we had to make some tables in order to determine the likelihood and the consequence of and the frequency of our, if anything was to occur in our process. So right here we just have an example of our HAZOP. And so for example, the C risk rating would come from a high frequency and a high consequence, and then exactly the same for B, just we'd have a very severe consequence if it was to occur.
And then next we'll get into the environmental aspect of mining operations, the first one being acid mine drainage. So this occurs when sulfide minerals become exposed to another medium, such as water or air. So this can have a number of side effects on aquatic life and as well as human life due to the toxicity. And then there's also the heavy metal contamination. Examples of heavy metal are lead, chromium, cadmium, mercury, etc. And each of these have their own unique health hazards to both wildlife and human life, such as carcinogenic implications, neural damage, etc. And then there's also chemical pollution, which is more related to our process in particular, since we're using cyanide. So this would go into water streams in particular. So there's certain environmental effects, such as it can be embedded in soil and water, which then affects wildlife through panting, uncontrolled eye movement, etc. There's also the effect on humans, such as headaches, fatigue, and could possibly end in death as well. Then there is erosion and sedimentation. So to properly reach an ore body for a mine, so actions need to be taken, such as stripping and contouring of the land, which can then cause the erosion problems of the land, which will then translate into water systems, which then can toxify the water. And then for the assessment, we also considered a pollution prevention plan. So we looked into 3 main methods. The first one being electrolysis, which uses electrochemistry to remove contaminants from water. We also use ultrafiltration, which uses a membrane filter, again, to remove contaminants and impurities. And for the cyanide aspect, actually many companies implement this. It's a natural cyanide degradation through volatilization, photodegradation, and as well as microbial oxidation. And then for the sociological assessment, there are 2 main negatives and there's 2 positives. The first negative being the implementation of this plant can have an impact on the local water supply due to those environmental impacts as mentioned before. There's also noise pollution that can occur. As for the positive side, the mineral processing and hydrometallurgy are actually more environmentally friendly when compared to other mining operations such as pyrometallurgy. Also, implementing a gold mine in Newfoundland Labrador obviously will exhibit provincial benefits. And then we get into the ethical assessment. So first one being the integrity, of course, and the safety aspects of the facility we're taking into consideration. Safety is not a priority, it's a core value. The PNIDs are also an essential aspect to this, as they incorporate many safety features. The design evaluation, which we explain a little later on, and then the ethical theory. So we looked into consequentialist aspects, so we weighed the benefit to harms. And then we looked into sustainability engineering. So first one was picking an optimal plant location, so there was minimal impact on society and the environment. We looked into selecting the best raw materials possible for the process, and also picking the best material to be utilized within the process to inhibit and mitigate corrosion. So next we'll get into the final plant design and then our team's recommendation.
So as you might have noticed throughout the process, or throughout the presentation, we've been talking a lot about flotation and hydrometallurgy. So we've actually done a plant design comparison to determine which was the better process for us to choose. So we based our comparisons on a production, economic, and HSE, and then we also had a no bias comparison. And right here you can see the no weighting bias on our comparison matrix here, and we have our weighted scores and a breakdown of the criteria and the descriptions, and give our final score to determine which was the best process. And so for here you can see we have our comparison bias. We have no bias, production, economic, and HSE, and you can see in the middle column here that flotation had the best score for all 4 of the biases and comparisons. So we have decided that flotation was our better design.
So that's the end of our presentation. Thank you for your time. If you have any questions, you can email one of us.